Hey guys, welcome to today's video on electron configuration. So in an earlier video, we looked at magnesium atoms and we were really focusing then on what's happening in the nucleus with the protons and the neutrons. Remember I mentioned that there is something called the strong nuclear force that keeps all of those positively charged protons crammed together in the nucleus. It keeps them from repelling each other and shattering the atom apart. There is also this Coulombic attraction, which is simply an attraction of positive to negative. And that attraction is the one that keeps the protons and the electrons together as a unit. The protons and the electrons are attracted to each other. That Coulombic attraction is the basis for what is known as Coulomb's law, which tells us that the force of that attraction, and I'm talking about between the oppositely charged protons and electrons, the force of that attraction gets stronger when the charge is larger, and that force of attraction gets weaker when the distance is longer. So we will be talking about this law over and over and over again throughout the year. But what I want to mention to you right now is that Coulomb's law would tell us that the force of attraction between these protons and these valence electrons out here would be kind of weak because the distance between them is so long. And flip side, the force of attraction between these protons and these electrons is going to be stronger because the distance between them is shorter. Okay, again, we'll be talking about that a lot more as the days go by. Alrighty, so now let us work on the main job of today, which is to move away from this really basic depiction called a Bohr diagram and get a little more sophisticated in talking about the electrons. In a Bohr diagram, we show the 12 protons in the nucleus and the 12 electrons in these concentric rings, or they're sometimes called shells. It's very basic. It shows here that there's only 2 electrons in this smaller shell or energy level. And as you move farther from the nucleus, the energy level is bigger and can hold more. All right, so what we have next is a set of boxes called orbitals. And this picture is collectively known as an orbital diagram. So what we're going to do is represent the 12 electrons of magnesium, and we're going to put them in energy levels which have sublevels which are made of orbitals. And the placement of those electrons is guided by 3 principles. First of which is the Aufbau principle. The Aufbau principle tells us that electrons fill the low energy orbitals first. So if I have 12 electrons, I know the first one I'm going to place down here in the first energy level, which has an S sublevel. Now, you know, I said down here because on this orbital diagram, it's physically at the bottom of the page. But this first energy level in this notation is the one that's closest to the nucleus. Okay, now I've placed only one of 12 electrons. The second electron is also going to go in this same box because an orbital has the capacity to hold up to 2 electrons. But I have another principle that I want to mention. It's called Pauli exclusion principle. And it simply says, if you are going to put 2 electrons in the same orbital, they have to have opposite spins. So electron number 2 is going to be depicted like that, just an arrow pointing down. Okay, so I've placed 2 out of 12 electrons. Here is number 3, and number 4 spinning in the opposite direction. Electron number 5 is going to also be in the second energy level, but now we have a p sublevel. And the p sublevel is made of 3 orbitals, each of which can hold 2 electrons. All right, so I'm going to put number 5 here. But number 6, I want us to look at the third principle, which is known as Hund's rule. And it says electrons won't double up in an orbital until they have to. And that's because of a property that orbitals have. We say that orbitals are degenerate. Orbitals, I'm sorry, let me qualify that. Orbitals in a sublevel are degenerate. That adjective means they have the same energy. So these 3 boxes, these 3 orbitals in second energy level, p sublevel, they all represent the same level of energy. So these electrons that are filling don't really have a preference for one orbital over another. This was electron number 5. Hund's rule says don't double up yet, so I'm going to put number 6 there. And I'm going to put number 7 there. And now number 8 is going to go back and double up, and number 9, and number 10. All right, thus far I have placed 10 of magnesium's 12 electrons. Look guys, look at the correspondence between the Bohr diagram, which is really simplistic, and this orbital diagram, which is a little more sophisticated. The first energy level had 2 electrons in both pictures. The second energy level can hold 8 electrons, and here they are. All right, so I've placed 10 electrons. Number 11 will go here, and number 12 right there. Now, the main reason that we learn how to do these orbital diagrams with all the up and down arrows is so that we can identify those substances which are diamagnetic and contrast them with those that are paramagnetic. Diamagnetic simply means a substance in which there are no unpaired electrons. I don't like that double negative. So think of diamagnetic, meaning all the electrons are doubled up. Okay, for example, neon with its 10 electrons is diamagnetic. Do you see how all the electrons have a doubled up partner? Diamagnetic substances, oddly, appear to weigh a little bit less in the presence of a magnetic field. Now, the other adjective we have is paramagnetic, which describes substances that have unpaired electrons. So I want to show you, for example, the element oxygen, which has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Do you see that there are 2 unpaired electrons here? So we describe oxygen as being a paramagnetic substance, and paramagnetic substances appear to weigh a little bit more in a magnetic field. All right, so now let's go back to our orbital notation for magnesium, and let's transform this orbital notation into an electron configuration. We start with the energy level closest to the nucleus, energy level 1, which has an s sublevel, and there are 2 electrons in it. Then we go to energy level 2, which has an s sublevel, and there are 2 electrons in that sublevel. But oh, energy level 2 also has a p sublevel that holds 6. And moving up to energy level 3, the s sublevel has 2 electrons. So if you wanted to double check yourself, these superscripts, which are the numbers of electrons, those should all total up to 12 for magnesium. And I want to point out one more thing. Valence electrons, or the electrons in the highest numbered energy level, 1, 2, 3, energy level 3, okay, these are the valence electrons. Those are the ones most likely to be involved in bonding during a reaction. And then everybody else, those in level 1 and level 2, that's known as the core. Those are the core electrons. Okay, let's do another one. Let's consider the element chromium, which has 24 electrons. So Aufbau principle says, put the electrons in the lowest energy orbitals first. So I'm going to put number 1 here. And Pauli exclusion principle reminds me, if you're going to double up in the orbital, they need opposite spins, 1 and 2, and then 3 and 4. And then Hund's rule says, oh yeah, if you have degenerate orbitals in a sublevel, don't double up until you have to. So this is 5 and 6 and 7, and then we have 8 and 9 and 10. I've placed 10 out of the 24. Let's keep going. 11 and 12. 13 and 14 and 15 and 16 and 17 and 18. Okay, I'm in the third energy level, which has an S sublevel, a P sublevel, and a D sublevel. But do you notice how 4S is squeezed in here between 3P and 3D? So it gets all kind of crazy funky at this point. Turns out that the 4S sublevel is really a little bit lower in energy. See my energy scale here? It's a little bit lower in energy than 3D. So I'm going to put number 19 here and number 20. And now I'm ready for 21 and 22 and 23 and 24. Can you see by looking at all of these unpaired electrons that this would be a paramagnetic substance? Alrighty, let's then transform this orbital notation to an electron configuration. Starting closest to the nucleus, energy level 1, sublevel S has 2 electrons. Energy level 2, sublevel S has 2. And energy level 2, sublevel P has 6. Then we have 3, S, 2, and we have 3, P, 6. I'm working my way right up the page. Next I show 4, S, 2, and then 3, D, 4. All right, now let's talk about the valence electrons. Valence electrons are the electrons in the highest numbered energy level. I've got energy level 1 and 2 and 3 and 4. Energy level 4 is the highest numbered. It's the biggest number. It's physically farthest from the nucleus. Because it's farthest from the nucleus, Coulomb's law is going to tell me that its force of attraction is going to be the weakest. It's going to be the most vulnerable for being removed in a reaction. All right, so I'm going to circle these 2 electrons in level 4. Those are my valence electrons. And everybody else, literally everybody else, is core electrons. Alrighty, now the orbital diagram that we've been working here with the up and down arrows does have its place, and it can definitely help us to identify diamagnetic and paramagnetic. but sometimes it's a little bulky. And sometimes really all we want to generate is this electron configuration. That's what this code is called. So to do that, we have some really cool tricks using the periodic table. So on my periodic table here, I've color-coded these first two columns, and that would include helium, and I've labeled it the S block. And this green part over here is my P block. Notice that the S block is 2 columns wide, and S sublevels can hold 2 electrons. Notice that the P block is 6 columns wide, and P sublevels can hold 6 electrons. This blue area that is 10 columns wide is the D block, corresponding to D sublevels that can hold 10 electrons. And then down here I have the F block, which goes across 14. All right, so let's do an electron configuration for tin, which is number 50, meaning it has 50 electrons. All right, so I am going to write the electron configuration using my periodic table as a guide, and I literally work from the top left to right and read it like a book. So when I'm up here in period 1, I am filling the first energy level. So I'm going to write 1s2. Boom, boom. And now I'm going to go down to the second period, and I'm going to fill up second energy level. So I'm going to write 2s2. I'm still on my second period, and I have 2p6. Now I'm going to move down to the third period, and in period 3, I'm filling the third energy level, so I'm going to write 3s2 and 3p6. Okay, now notice I'm down to period 4. This is the first time I'm encountering the D block. So as I move across period 4, I'm thinking, okay, fourth energy level, that's going to pertain to the S and the P. Do you see a little bit of color coding that I did here? I did yellow and green. So when you're in the S block or the P block, you are filling the energy level that matches that period. But for the D block, that's not the case. Let's just look for a minute back at our orbital diagram. Remember that when you, let's see, how do I want to say this? The 4s is going to fill up before the 3d. So let's see how that plays out. Okay, I am at the beginning of period 4, so I'm going to write 4s2, but after 4s fills up, then 3d fills up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I get back to the P block and I'm back here on fourth energy level, 4p6. Let's go down now to the fifth period, and I'm filling the fifth energy level, 5s2. But when I hit the D block, I am no longer in the fifth energy level. I'm back in closer to the nucleus, and I'm in the 4D block. So in my period 5, this is 5s, but this is 4d. I move all the way across, all 10 of them, and now I'm back in the green. I'm in the P block, so I'm back on 5p12. Okay, that is a very long electron configuration. The highest numbered energy level, the energy level that is physically farthest from the nucleus, is level 5. So the electrons in level 5, these 4, those are your valence electrons, and everything else is core. Now, you may remember from last year that we had a shorter version. Another way that I can write an electron configuration for 10 is not start up here at the very tippy top, but instead I can go to the previous period and go to the end. This Kr, krypton, is a noble gas. So I'm going to say all of this stuff is essentially the electron configuration of krypton. Now I'm hopping down to period 5, and I'm going to finish up with 5s2. When I hit the D block, I go a little bit closer, 4, D10, and then I'm back here to 5p2. This notation is called the noble gas configuration. Most of the time it is perfectly fine for you to use that, but on the AP exam, if they ask for a complete electron configuration, you have to start at 1s2. Alrighty, so the purpose of writing an electron configuration is for us to kind of get a sense that life is not so simple as the Bohr diagrams would imply. Each of these energy levels have different distances from the nucleus, but they also have some complexity of their own. So let me just talk to you briefly about a gentleman named Heisenberg, who said, okay, we're dealing with electrons. We know that they are very tiny particles, but they also have some wave behavior. So as he contemplated that weirdness, electrons are particles that sometimes act like a wave, he acknowledged that the electrons are also constantly moving. And so he decided, and this truth, this principle has been widely accepted, he said, you know what, it's impossible to know both the exact location of an electron and its momentum, or how much energy it has. You can't know both. So you have to pick one or the other. And because electrons are zipping around constantly, we in chemistry have decided, you know what, let's not try to pin them down and say their exact location. Let's just settle for sort of a fuzzy area where they probably are, and instead focus our attention on their energy. So then next came a physicist named Erwin Schrödinger, and he used some very advanced calculus to describe the energy of electrons in terms of math equations. And these equations that he came up with yielded an answer that is a wave function. And the wave function is also called an orbital, and it has a shape. So before you get too crazy with this is very advanced math beyond the scope of what we're doing in a first-year college chemistry class. But we're just saying, you know how you can write an equation for a line? Well, you can also write an equation for a parabola. And then in calculus, you'll learn that you can write equations that describe 3D shapes like cones. Well, Schrödinger used his advanced calculus, solved these equations for the electrons and their energy, and came up with shapes. So in the first energy level, the nucleus is where the X, Y, and Z axes intersect. And then around that nucleus, see that little sphere? That's the 1s orbital. That's the region where those two electrons are most probably found. Most probably. We're not going to say certainly, but they're probably somewhere in that sphere. When we go out to energy level 2, S sublevel, the answer to the equations, the wave function, yields another shape that is spherical, but it's a little bit bigger, farther from the nucleus. And the two s electrons are zipping around, most probably, in that sphere. And in the 2p sublevel, each of those orbitals is kind of like a dumbbell shape, one that's oriented on the x-axis, one that's on the y, and one that's on the z. And collectively, those make up the 2p sublevel. Remember, these orbitals are degenerate. They are all equal to each other in energy value. All right, then the third energy level has an s sublevel, which is again spherical, but it's bigger. Here's the 3p, which has those dumbbell shapes oriented x and y and z, and they're bigger. And then we get to the d sublevel, and these shapes, which are not made up by a crazy person, they are the solution to these calculus equations, and they're very funky looking. So the good news is you really don't have to know a whole lot about this, certainly not the math that generated these shapes, but simply to know that this model of where the electrons are, it's called the quantum mechanical model, and it really strives just to acknowledge that the electrons in an atom have different energies. And we're going to focus on their energies rather than pinpointing their exact location in space. So it's important that you can use your periodic table to generate an electron configuration, either complete or abbreviated using a noble gas. It's important that you be able to do a rudimentary orbital diagram so that you can identify substances that are paramagnetic or diamagnetic. Okay, guys, that was a lot. I hope that was helpful. Thanks.